So let's talk about we had talked about vorticity. Here we will talk about circulation. Circulation and vorticity are related to each other. And so if you just think about probably a mass element here, this is a body fluid, and this body fluid actually has some surface, okay? So this has a surface S, and this at the location somewhere here at a 90-degree to the surface, you have a unit vector N, and let's suppose this is enclosed by the line at C, and there is a small segment here that goes from here to here, and that is small segment ds. Okay, it's a vector. And what you have is, at this location, you also have a velocity v. Okay, so then here what you have is, this represents nothing else than the closed path. So by the closed path, we mean the path that is enclosed to the surface. Then S is the enclosed area. Okay. Then the net rotation around this loop, we're going to call that the net rotation is what we're going to call circulation. Okay. And we were going to define the circulation by gamma, is gamma c, and is going to be equal to a circulation and over psi, over this line, velocity v times s dot. Okay, so if we understand a few things here, first of all, the difference between vorticity and circulation. Vorticity, as a review again, vorticity is nothing else, is defined by omega, if you remember, times 2 times the rotation, which is equal to the curl of v. And this is nothing else than the measure of the rotation of a fluid element as it moves through the flow. Okay. Now, this is vorticity. We talked about this, right? So the circulation, on the other hand, is and we're going to show you soon that these are actually related to each other. And I just gave you this definition in the previous page, and I will tell you how this actually works together. And we said this is counterclockwise integral. Okay, it's a counterclockwise line integral because that's why I put the arrow in this direction. And what is the circulation? It is nothing else than the line integral of the tangent of the tangential velocity component about a closed area. Closed curve. Fixed in the flow. Okay, so that's what exactly what I defined for you in the previous slide. So there are a couple of things that we can relate one thing and the other another. And what we could do is we could use the Stokes theorem. And this comes from your calculus classes. And this Stokes theorem basically states the following. You have a counterclockwise line integral that's equal to this. And we can show, and I'm going to skip all the derivation for this in this particular lecture, that this is actually equal to the enclosed surface times the curl of V dot ds. Okay? So the couple things that you have to keep in mind. First of all, if you recall, again, this over here from your previous lectures, this is nothing else than your vorticity. Okay, this is a vorticity vector. So what we are saying is that your circulation is also equal to the double integral over my enclosed area of my total vorticity acting in the surface is dot ds. Now, my dot ds, I can express this ds as the following. So I could take ds and find the unit vector, right? So I could take ds and I divide this ds s divided by the vector s, right? So this will give me a unit vector times ds. Okay, so now what you have basically done is you have taken the unit vector of this and expanded. So in that sense, I can say that ds is actually equal to the unit vector times ds. Okay, so we can express this whole thing as dot product times my unit vector times my surface area ds. Okay, so in this sense, I could define the using the Stokes theorem, we could define vorticity as follows. We could say this is the flux of vorticity across a surface bounded by the loop. Okay, so basically Stokes theorem, let's talk a little bit more about Stokes theorem, and then we will go and move into a couple of applications and we'll do some numerical examples. Okay, Stokes theorem says basically, let's suppose we have enclosed path. Closed path, let's call this curly C. Okay, and this enclosed path, let's suppose we can express it like this, where this is your enclosed path right here, is right here. Okay, so this is a surface, but this whole surface is enclosed by this path defined by this path right here. Okay, this is your path. This encloses this path around this this circle here. Okay, so basically what we can say is this over here is we are saying that we can have an infinite number of of surfaces S, and all bound by your line psi. So this could be S1, this could be S2, and yet we are all saying that they're going to be all bound by the same enclosed area, okay? So also the next thing that we keep in mind is now if we choose if the chosen surface S is such that psi becomes a point, let me explain that. Now, if the chosen surface S is such that psi C becomes a point. So let's suppose we have this, okay, and we want to basically reduce this to a point. So I have this, I got this whole surface, and this area right here is enclosed by a ds. This is surface S, and I want to reduce the whole thing to a point, okay? So let's suppose this is my new enclosed area. Everything has reduced by this. So all this is bound by this surface right here. Okay, it's bound by that. If it's bound by the circle, by this line here, then what we have done is basically, and we want to make this smaller and smaller and smaller, we want to reduce this to a point. Then what we are basically saying is this integral that you have here, also the circulation in that point, around the point, will be actually zero. So it tends to zero. So what we can say in this particular problem, in this case, that your Stokes theorem, sorry, to forget this, your Stokes theorem basically is the velocity vector times S, and it's the same as a surface times omega dot n ds. This is all equal to 0. Okay? So there's some application of the Stokes theorem here. Now, third case, how do we actually apply this? So let's consider the following case. Now, for this particular case, case number C, let's suppose we have a flat plate. Okay, and this flat plate looks like as follows. So I have a flat plate. In this particular flat plate, X goes in this direction. This is your flat plate here. So this is your plate. Let me write this in a different color. This is your plate. And then we have vortex lines. Remember when we say vortex lines, we are talking about lines that go like this, and they have vorticity around this, right? So you had different vorticities that go around this. Then you also have a boundary layer that goes like this. And let's suppose I take a small segment of the boundary layer. Through that boundary layer here, you're going to have many, many different segments of vortex lines. Okay? And what we can say is here at the bottom, the velocity here at the bottom at the surface will be 0 because of no slip conditions, if you remember that. Okay? So the question is, in what direction is the vortex? Okay, so in what direction is the vortex? Okay, so if I'm going to draw, really check the vorticity, if you look at it, what's happening is the following. So I can have my vortex. Let me just draw this bigger here. Next, let me go to the next slide. So I am going to go ahead and take this small element that I drew here, okay, this small element and this element, and see what happens to it. So let's take this segment, and we know that we have the boundary layer. We got your flat plate, and what we're going to have here is we are going to have a boundary layer that actually is going to do something like this. So this is a velocity v at the top, and then I have a small element there, okay? Because I have a velocity v at top, here this is stopping, is making an opposite motion. So what's really happening on this segment here is doing this, okay? Because you can think that I'm taking this and pulling the fluid here while it's keeping it tight here, okay? If you're keeping something, think about your yo-yo, right? You got this, and you have a yo-yo, and this is coming at the velocity here. So what this is trying to do is trying to rotate in this direction, right? If you're holding this right here in the middle, is rotating like this. So it's the same idea. So this is coming in this direction, it's trying to hold together here, and this creating the vortex lines. So here, what's going to happen is many different points. As this becomes very, very, very small, you're going to have many different vortex lines that are going to go like this, in this direction. Okay? So these small vortex lines, okay, this is what your angular velocity is going to look like. Okay, that's your small vortex. Now, the vortex field can point in any possible direction. So let me write this down. The vortex field can point in any direction. Okay. So let me show you as for an example. So if I had a boundary layer sheet L, we can have infinite number of vortex lines. So consider this. So I can have, think of this, a vortex tube, okay? Inside this vortex tube, now I have, and what you can see is this is the boundary layer, right? This is your boundary layer that's going here. This is the boundary layer. And this is what your boundary layers forms, right? And it goes all the way to, you know, wherever this plate ends here, somewhere there. So it does something like this. And then inside this, you're going to have many vortex tubes. So here what you're going to have is, think about this, that each one of these lines is going to have, each one of these lines is going to have its own vorticity. So, so what I am saying is, whenever I use a double arrow, okay, I'm using a right-hand rule where I'm saying this is actually pointing in this direction. Your thumb is pointing in this direction, okay? So this is actually equal to this. Okay, that's what I'm trying to say. So this is actually equal to a line that's going in this direction, and along that line you're going to have a vorticity that goes in this direction. Okay, you're going around this clockwise, so you're creating that motion. Okay, so I can have that. So when you add all this, if I'm adding all this, all the vortices around here, different vorticities around this enclosed area that I have here, enclosed this loop, that will give me my total circulation. Okay? Let's consider another case, a case number D, let's say. In this particular case, let's suppose we have a cone and it's spinning. So let's consider the following spin. Okay, so now in this particular example, what we're going to have is, let's consider a cone, okay, and this cone is actually rotating. This cone is rotating, and then this over here is nothing else than my vortex line. It's my vortex vector. Note that this vortex vector is going to act opposite of the rotation of my of this fluid right here. But this is the speed at which this is rotating. Okay, this is the cone is moving, but my flow is going to move in the opposite direction. Why? It's going to move in the opposite direction because of Newton's second law. It has to move in the opposite spinning direction. Okay, so you can say direction. This is the direction of the spin. That is nothing else than opposite of the cone's spinning direction. Okay? So you have this flow that's coming here, right? You have all this flow that's coming here, that's moving here, is moving here. Let's see what happens in this segment right there, okay? So in this segment right there, you're going to have a flow pressure. You're going to have this flow pressure, okay? But then the cone is going to make, this is the cone, okay? This is the cone right there, and it's going to stop the flow. So what's going to happen when I'm trying to stop the flow? This flow has to go somewhere. And so what's going to end up happening is it wants to still go there. It doesn't know what to do. And it's going to end up spinning. Okay. That is right here. This motion there is what we call the vortex direction. That's why it goes in this direction. That's why this is happening here. This is the vortex direction. Okay. So this is a overall view on how vorticity and circulation work. In the next one or two lectures, we'll do a couple of examples to see how do we actually use this vorticity concept with circulation.